this is the Alps. This is a group of mountains that are located in the central Europe, and this picture is somehow located in Switzerland. So this is one of the most beautiful destination. So the Alps. Have you ever wondered how the Alps was formed? How about the Rocky Mountains in North America? Do you have any idea how these mountains were formed? Why they are tall? Right? We have the Himalayan mountain range that are located in the Nepal, Tibet border. So the tallest peak that is located here is the Mount Everest. So the Himalayan mountain range. So have you ever wondered how high this Mount Everest is, and does it continue to grow over time? We have plateaus. Plateaus are landform that are elevated and leveled on top. So how are these majestic landforms? How is it possible that these majestic landforms are formed? Okay. And we have plains. Plains are flatlands. These are flatlands. Most of the time they are used for agricultural purposes, and one of the majestic plains that are found in this planet is the Great Plains in North America. And we have the ocean basins. Alright, so have you ever wondered why ocean basins are deep? There's no ocean basins that are shallow. And if you compare these ocean basins in terms of how deep it is, so most of the ocean basins are deep compared to the landforms that we have that I have shown you earlier. So these are the things that we will going to have in this video lesson. Alright, so those are the pictures of the Alps, the Rockies, the Himalayan mountain ranges, plateaus, plains, and ocean basins. Now the question here is, what makes a place so elevated, and what makes a particular place deep, right? So that is what we will going to find out today in this video lesson that we have right here in Science 4K.
Science 4K.
Alright, so here we are in our topic for this video lesson. So to explain how these places became so elevated and some places that are considered to be deep, so we will go to a particular concept which might explain this process. This is the principle of isostasy. So what do you mean by isostasy, and what are the things that we can learn from it? Alright, so before we go to this one, let us recall the things that we have discussed before. We have the crust. Alright, so we will focus more on crust and mantle in this video lesson that we have right here. So the crust, this is the place where we live. So if you don't know this topic yet, so there is a link above this video. You can go to that particular link and watch the different layers of the Earth. All right. In that video, I discussed there the different layers of the Earth and their distinct characteristics of each layer. All right. Going back to the crust has two divisions. So we have continental crust and we have the oceanic crust. So in terms of characteristics and other stuffs, continental crust is different from oceanic crust. So the first one, we have the thickness. Continental crust is thicker than the oceanic crust. Then we have in terms of density, we have the continental crust being buoyant or less dense. So the oceanic crust is somehow denser than the continental crust. Now in terms of age, oceanic crusts are younger than continental crust. So that's it. That is their differences in terms of their characteristic. Now, basically, the crust is the thin layer of solid brittle material that's the outermost part of the Earth. Alright? So this is where we live, and the crust is always subjected to different exposure to changes, all right? Like subductions, volcanic eruptions, earthquakes, so on and then so forth. Okay, so those are the things that makes the crust changes its shape over time. All right, so the crust is different depending on where you live. So as I've shown earlier, we have the oceanic crust and then the continental crust, which considerably different from each other. Alright, and in terms of the velocity of the seismic waves travel faster in oceanic crust than in continental crust. Alright, so let me know in the chat box or let me know in the comment section, why do you think that seismic waves travel faster in oceanic crust than in continental crust? Alright, so the reason of which is seismic waves are faster when the material is said to be denser, right? So that's the reason why the seismic waves travel faster in oceanic crust than in continental crust. So last time also, on that video, I managed to show you that the continental crust is made up of granite, and most of the continental crust is made up of silicon and aluminum respectively. And on the other hand, we have the oceanic crust, which is made up of basalt, and basalt are dark in color, and most of the oceanic crust is made up of silicon and magnesium respectively, right? And the boundary between mantle and the crust is called the Mohorovic Discontinuity in honor of Andrija Mohorovic. Alright, so he's the one who described that there is a dense region between crust and mantle that changes its density, and it affects the velocity of the seismic waves. As the material gets denser, the seismic waves velocity got faster, or it is increased several times. All right, so below the crust is the mantle, which is more dense than the crust. All right, so technically speaking, that the crust is floating above the mantle. All right, and what we have right here is the granite composition of the continental crust and the basalt composition of the oceanic crust. So these two crusts are the same but different in composition and also with their characteristic. Alright, so also last time I included also some special layers of the earth, which is called the asthenosphere and then the lithosphere. So asthenosphere, this is the upper layer or the part of the upper mantle which is said to be free-flowing and viscous, right? And on top of it, there is a layer called lithosphere, and lithosphere is made up of layers of crust and upper mantle. So this lithosphere is the foundation of the plate tectonics. That will be a video for another day. And this plate tectonics is the main factor of changes here in the Earth's surface. It promotes earthquake, volcanoes, and mountain buildings as such in order to form different majestic landforms like what you have seen earlier, the Rocky Mountains, the Mount Everest, the plateaus, the plains. Those landforms are possible because of the action of plate tectonics. Alright, so today, what we will going to have is this iceberg, right? So what is this iceberg all about? So aside from what this iceberg is all about, and can we use this iceberg to explain how the changes in elevation happens to every places here on Earth? So before we discuss how that process is possible, we should take note first some keywords that we might encounter along the way. So the first one is density. Density is a property of every matter. Alright, so density. Now, density is described as the relationship between mass of the substance and the space that it takes up. Simply, volume. Alright, by dividing the mass over volume, you will get the density of an object. Alright, so density is very important in determining the next part, which is the buoyancy. Alright, a less dense object might likely to float, and a more dense object will likely to sink to a certain fluid. Alright, so buoyancy is described as the force that is exerted by a fluid that opposes the weight of an immersed object. Alright, so if you are standing here on Earth, the force of gravity, that is your weight, is the manifestation of the force of gravity acting on you. When you are submerged on water, when an object is submerged on water, the force that is experienced by the object as you put it on the water, that upward force is called the buoyant force. Alright, so it is simply written as F sub B, and the weight is written as W. Alright, the weight is. Alright, so this is buoyant force and this is weight. Then both of them is explained by mass times gravity. Alright, so both of them are explained by mass times the gravity. So that is buoyancy. Buoyancy was first described by Archimedes, right, during the certain era, alright, certain time. So it was discovered by Archimedes, and it is the working principle of why ships floats. They do not sink. Why the ships, even though it is more dense, the steel is more dense than the water, the seawater, why does the ship doesn't sink after all? Alright, so density and buoyancy is the main concept that we will have as we discuss the formation of the different landforms here on Earth. Alright, so the question that we will first ponder is, what causes Earth's varied topography? Alright, so when we talk about topography, this is the formation, land formation. Alright, so there are plateaus, there are plains, there are mountains, there are rivers, there are oceans, alright, trenches, something like that. So what makes this varied topography possible? Alright, what causes this varied topography? Mainly, what we are going to talk about here is the elevation. Alright, so we are talking about here the elevation. Why there are some places that are elevated, why there are some places that are not elevated. Alright, so in order to understand the things that we will going to answer that question, alright, so I have here a simple experiment that will explain different things. Alright, so in it, we have here the concrete slab of thickness, alright, or not that thick at all. We have here a wooden block, which is the same thickness as the concrete slab. So we have here a wooden block which is thicker in Y dimension. Also a not so thick wooden block, and also a bowl of beans and kernels, corn kernels, and we have the water itself. Alright, so the water, that is very important here. Now, what are these materials all about? So the question here is, what does this represent in the Earth system? What does this material represents in the Earth system? Can you put your answer in the comment section of this video? Alright, so let me know what do you have in mind before I reveal the answer. Alright, so what are the representations of the things that we have right here? Now, these materials that you have, the concrete slab and the wooden block over here, the same thickness with the concrete slab, and the thicker version of the wooden block, alright, and a small wooden block, and this one, the beans and then the corn kernels, this represents the crust. Alright, so this represents the crust in different variations. One that is thicker, one that is denser, one that is thinner. Alright, so these are represented by crust. So the oceanic crust and continental crust mainly. Alright, now how about the water that you have right here? So the water that you have right here represents the mantle. Right? So that's right. It doesn't represent the ocean, the water from the ocean, but it represents the mantle itself. Alright, so now, what do we have right here? Alright, so we will going to demonstrate how isostasy works. Alright, so the first thing that we will talk about is the density itself. Now, how does the density affects this process? Okay. Now, I have right here, I submerge first. Right? I submerge first the concrete slab in the water. So, alright, so this one. So, what do you think will happen if I put the concrete slab on the water? Will it sink or will it float? Alright, so write your answer in the comment section of this video and let me know what your thoughts about this simple experiment. Alright, so let's play. So as I put the concrete slab, the thin concrete slab on the water, it definitely sinks. So it means that the concrete slab is denser than the water. Alright, so the one that you have right here. Alright, so the question here is, what does this concrete slab represents? Alright, so definitely it represents the crust. So what division of the crust does the concrete slab represents? Alright, so put your answer in the comment section. Okay, let me know your thoughts about this. And this concrete slab is representing the oceanic crust. Alright, it represents the oceanic crust. So it means that it both shares the same density with the oceanic crust. Oceanic crust is somehow denser than the continental crust, and since it is denser, it sinks on the mantle. Alright, it sinks on the mantle, and the places where there is an oceanic crust tends to be deeper than usual. Alright, so it tends to be deeper than usual. Now let's go to the other one. So I have right here a wood. Alright, so I have right here a wood of same thickness as the concrete slab. But if I put it on the water, what do you think will happen? Right, so let me know what do you think will happen if I put this wood on the water. Right, so let's put it on the water. Alright, so it floats. Okay, so the wooden block floats, and even though I try to push it further, alright, in the water, it doesn't sink in the process. Okay, and it goes back. As I push it, it goes back again to the surface. So definitely this wooden block is less dense than the water. So what does this one represent? It represents the continental crust density. Okay, it represents the continental crust density. Now, as the thickness, it doesn't represent the continental crust in terms of the thickness. It is somehow thinner compared to the continental crust. Alright, so let's take a look another portions of this experiment that might lead us to the answer why there are varied topography here on Earth. Alright, so I have right here the wooden block. Alright, so the wooden block, which is not that thick compared to the other one that will be next. So if I put it on the water, so if I put this block on the water, it will float. So the reason why I holding this wooden block is because it tends to find its center of gravity. It tumbles down. Right? So it tumbles down. It the wooden block finds always finds the center of gravity. So that is why in order to achieve its gravitational equilibrium, alright, or gravitational balance. It's the same thing as the landforms here on Earth, alright. So the thicker the wooden block, alright, so the more part of it will be submerged underneath the water. So in our case, we have here the mantle, or the water represents the mantle. Alright, and also, the reason why the mountains doesn't tumble down, like the one that you have right here, it's because it is constantly in balance. Alright, so that's right. It is constantly in balance. The gravitational balance up top of the mountain and the bottom part of the mountain should be balanced in order not to topple down. Like the one that you have right here, if I release this wood, eventually what will happen to this wood is it will tumble down, and as it tumbles down, it will find its center of gravity. Alright, so in this case, I continue to hold it, and I feel the buoyant force coming from the water, okay, resisting or applying. Alright, so the buoyant force is being applied on the wooden block that I am holding right here. That's the reason why you will see the wooden block that I have right here, it starts to go in a diagonal position, right, from time to time. Alright, so that's the wooden block. So as you can see, it is submerged at the bottom, and if the wooden block is denser or less dense, it floats higher above the water. Alright, so let's take a look at the other wooden block. Okay, so right here, I have a much thicker wooden block. Okay, a much thicker, much larger wooden block. And as you can see right here, this wooden block also experienced the buoyant force, the same force that we experienced in the previous wooden block. So as you can see, it is submerged. Alright, submerged partly at the bottom that you have right here, and there is something on the top. So landforms like mountains look like this. There is something on the top, and there is something at the bottom. It's roots. Alright, so the roots of your mountain. Okay, now the reason why mountains have roots, it's because that roots is for one purpose, for balance. Without the roots, the gravitational balance between the top portion of the mountain and then the bottom portion of the mountain will be imbalance. What will happen to your mountain? It will tumble down in different direction. Just like what I have right here, I am still holding this wooden block. I'm still holding this wooden block over here so that it will not tumble down. Alright, it will maintain its balance upright. Alright, so again, in terms of density, now if an object is less dense and it is thicker, it will float higher above the mantle. So the one that you see right here, the wooden block is less dense than the water, so it floats higher above the water. Alright, so in this case, we have the roots over here and the top portion. Alright, so the top portion is the one that is most of the time, that is the peak of the mountain. Alright, so the mountain that we see in our naked eye. Okay, so that is the wooden block, the case of the wooden block that we have right here. Okay, right, now those situations that you see earlier, these are best explained by a concept known as isostasy. So what do you mean by isostasy? This is a balance or equilibrium, right? It is best described as balance of or equilibrium as the crust floats above the upper mantle, right? So as the crust floats above the upper mantle, the crust itself is maintaining this balance, alright, or equilibrium. Okay, it maintains its balance and equilibrium just for one purpose. It is not to tumble down. Alright, so it is not to tumble down. So imagine if you have a mountain as tall as this and there is no gravitational balance between the mantle and the crust, what will happen to this mountain? It will tumble down. And as you can see right here, the higher the mountain, the deeper the roots it contains. Okay, why is that so? Right, so why is that so? Why do we have a deeper roots when the mountain is so high? It's because we need to maintain that equilibrium, right? So without these deeper roots, these mountains will likely to go upside down. Alright? So as you can see right here, it maintains its equilibrium at different depth. Alright? At different depth, it depends upon the thickness of the continental crust. And meanwhile, the oceanic crust, since it is less dense and thinner, it doesn't need a root. Alright? It doesn't need a deeper root just to anchor itself to the mantle. Right? So that's the thing about the oceanic crust. Okay. That is isostasy, and that's how the isostasy works in the mountain building process. Alright? Alright, so that is the isostasy, and the next thing that we will take a look is the density. Alright? So the isostasy already explained the thickness, how the thickness of the continental crust and the oceanic crust affects the formation of different landform. Now, the thicker the crust, the thicker the continental crust, the higher the elevation of a certain place there is. Now, in terms of the oceanic crust, since it is thin, so it means that the elevation of that certain place that contains the oceanic crust will likely to be deeper as usual. Alright, so in this case, we will talk about the density itself and how does this density affects the formation of different topography here on Earth. Alright, so we have right here the pine and then the oak tree. As you can see, both of them are submerged in the water. So both of them are submerged in the water, and we can say that the oak, alright, so we can say that the oak is denser than the pine tree or the pine wood. Alright, so this one is less dense. Alright, so that is, we can safely say that assumption. Why? It's because the oak wood sinks, alright, sinks lower than the pine wood that you have over here. So since it sinks deeply on the water, so it means that it is more dense than the pine wood that you have right here. So as I said earlier, if you have a thicker object and it has a less density, all right, if the object has less density, it will float higher above the water. So in this case, the pine wood, all right, so the pine wood floats higher above the water because it is less dense, right? All right, so in terms of density, right? So in terms of density, continental crust varies in a small amount. In just a small amount, the continental crust varies in just a small amount in terms of density compared to oceanic crust. All right, and the density of the upper mantle is not that high, right? It is not that high, and or it is just a small difference between the continental crust and then the oceanic crust. So it's just 3.3 grams centimeter or cubic centimeter. So this is the density of the upper mantle compared to the crust and then the oceanic crust. Alright, now as you can see right here, that the crust is, based on the definition of the isostasy, that the crust is floating above the mantle. So the crust is floating above the mantle. So it means that the continental crust and then the oceanic crust is not totally submerged on the mantle. It is partially submerged on the mantle. Alright, so if we will going to compute how much of the crust is partially submerged to the mantle, and how much of it or how much of the oceanic crust can be seen on the surface or of the mantle, alright, something like that. So there is a mathematical expression that we will going to use in order to prove that particular aspect. Alright, so these are the partially submerged object. Okay, so when we talk about partially submerged object, just like that you have right here, the pine wood and the oak wood, so these are partially submerged object because one part of these objects that you have right here is submerged at the bottom of the water, alright, it is submerged beneath the water and some parts are on the surface of the water. Hence, they are called partially submerged object. Now, partially submerged object, especially the one that you have right here, the ships. Alright, so if you may ask, this is counterintuitive. Why do ship floats? Alright, so why do ship floats? It doesn't sink at all. Even though it is somehow massive, just like this aircraft carrier and the cruise ship that you have right here. These are massive ships and still they float. They do not sink after all. Alright, so it is because of one thing. Alright, so before I reveal the answer, let me know in the comment section, what do you think is the reason why ship floats over water? Alright, now the reason behind is the air pockets. Alright, so the air pockets that are located inside this ship. Alright, so the air pockets that are located inside this ship enables this ship to float above water. Alright, it floats above water. So this air pockets equalizes, alright, so equalizes the buoyant force acted by water to the ship and the weight which is acted by the ship to the water. Alright, so it equalizes the buoyant force and then the weight respectively. That is why even though it is a massive aircraft carrier or a massive cruise liner that you have right here, as long that the weight and the buoyant force between this object, right? So the forces between weight and buoyant force is equal, therefore the ship will continue to float unless there is a breach in the hull, right? There is a breach in the hull of the ship, and the water gets inside, and then these air pockets will suddenly disappear. Okay? When the air pockets disappear, then the ship will likely to sink because the weight of the ship, alright, the weight of the ship is greater than the buoyant force that the water offers to the ship. So instead of floating, the ship will likely to sink. Okay? So that's how this massive objects floats above water. Alright, so the partially submerged object was described by Archimedes Principle. Alright, according to Archimedes, any fluid exerts a buoyant force. Okay, whether it is an oil, a water, an alcohol, alright, or any fluid, alright, any fluid. It exerts a buoyant force on the object. Right? Just like the mantle and then the crust. The mantle exerts buoyant force to the crust. Right? Although it is not the crust is not submerged all throughout. It is partially submerged. It is just partially submerged. Now, the buoyant force equals the weight of the fluid displaced by the object. Alright? So in this case, if you take a look at this one, the weight of the object on air is 7 pounds. Right? So this thing over here. Now, when we put this water on, or when we put this weight, alright, when we put this mass on the water, suddenly the weight decreased to 4 pounds. What happened to the 3 pounds? Right? What happened to the 3 pounds? The 3 pounds is the buoyant force. The 3 pounds was countered by the buoyant force of the water. Alright? So, since this is going to different direction, so this is the weight and this is the buoyant force, they are opposite in direction. So, if you subtract the buoyant force and then the weight, alright, so it will likely that the mass that you have over here will likely to somehow register as 4 pounds. Okay, where does the 3 pounds went? Alright, where did it went? Alright, so the 3 pounds, alright, so the 3 pounds extra mass of your weight over here is the displaced water. It is the displaced water after submerging the weight on it. Right? So this is the water that overflows in the process. Alright, so if you measure that water that overflowed, alright, if you measure that water that overflowed in the process, it is equivalent to somehow more or less 3 pounds. Alright, it is equivalent to the 3 pounds or equivalent to 3 pounds. So this is the displaced water. Now, in case of the ship itself, now, why does the steel ball sinks when ships are not? Alright? Why does the steel ball sinks when the ships are not? Alright. It's because the displaced weight of the ball is less than the ball itself. For example, the ball has a mass of 1 kilogram. Alright, for example, the mass of the ball is somehow, example, 2 kilograms. Meanwhile, the force, alright, so the force of the buoyant force of the water is somehow 1 kilogram only. Is for 1 kilogram only. Right? So the force of the water is, or the buoyant force of the water is 1 kilogram. So there is a difference of 1. There's a difference of 1 in terms of their forces. So what happens here is the buoyant force cannot counter the weight of the object, then therefore it sinks. Now in the case of the ship, the displaced water is equal to the hull weight. So meaning to say, because of the air pockets located inside the ship, because of the air pockets, the displaced water, if this is 2 kilograms, the displaced water is also 2 kilograms. Therefore, it equalizes and balances out the ship. It doesn't sink. Therefore, it will float above the water. Since the buoyant force is equal to the weight of the object. Alright, so that is the Archimedes Principle. Right? So the buoyant force of an object, wholly or partially submerged, the magnitude of the buoyant force equal to the weight of the displaced object. So always take note that when the weight is greater than the buoyant force, it will sink. Always take note. Alright, when the buoyant force is greater than the weight of the object, it will float. Right? So it will float. Okay, so that is the partially submerged object, and let's calculate some sample problems. Okay, related to the partially submerged object. Alright? Alright, so we have here the first sample problem related to partially submerged object. Now, if you want to solve it on your own, alright, and you can pause the video. You can pause this video if you want and solve this problem before I reveal the answer. Alright, so you can do that one. Alright, so let me read the problem. The iceberg is somehow 917 kilogram cubic meter in terms of density, and it floats in seawater, which is 1025 kilograms per cubic meter. Alright, that's the density of the seawater. What is the fraction of the iceberg that is beneath the surface of the water? So we are talking about this one over here. Okay. And what is the fraction of the iceberg that is above seawater? Right? So what is the fraction of the iceberg that is above seawater? Now, in order to solve this one, okay, so let's take a look. The iceberg is floating on the water. So it means that the buoyant force is somehow equal to the weight of the object. Alright. Now, how do we compute the buoyant force? We compute the buoyant force as mass times the acceleration due to gravity, and also with the weight that we have on the other side. Alright, so the mass. Now, in terms of this one, we have here the mass of the fluid, and at the same time, alright, so mass of the fluid and mass of the object on the, as a whole. Alright, so in order to find out what is this buoyant force, so we need to use the formula of density over here. So we can get the formula of density as mass over volume. Now, since we are looking for the mass in the formula, so we will rearrange this formula, giving us the P times V times G. Alright, so the P over here is the density of the fluid. The V over here is the... Alright, so the V over here is the volume of the submerged object. Right, so that's the volume of the submerged object. This is the Vs. Right, so V sub S. And the acceleration due to gravity. Meanwhile, on the other side, so mass. So how do we compute the weight of the object using the density formula that we have right here? Again, we will going to use P times V times acceleration due to gravity. Alright, so what is this P all about? This is the density of the object as a whole. So the whole iceberg over here, the density of the iceberg. And we have right here the volume of the object. It means the volume of the whole iceberg. Alright? So it means the volume of the whole iceberg. Now, canceling out the G over here, we can get the formula PF is equal to, or rather, PF is multiplied to volume of the submerged object and submerged part of the object and density of the object times volume of the object. Alright, now to compute for the fraction, so since we are looking about the fraction here, so in order to compute the fraction, we need to find out the fraction between volume of the submerged part of the object and the volume of the object. So this is the fraction that we need. Now, in order to compute that one, we need to divide both sides by V sub O. Right? So, divide both sides by V sub O. So, cancel the V sub O. Right? In the process. And since we have PF over here, divide both sides by PF. Alright? So, PF is also canceled. The pressure of the density of the fluid. So, we can get pressure of the object, or density. Alright, so P stands for density. Alright, so density of the object divided by the density of the fluid. Alright, in order to find out the fraction, alright, the fraction of the submerged part of the iceberg and the fraction of the iceberg that is above the surface of the water, we need to use this formula. Alright? So, let us rewrite again this formula over here. Alright, so we have V sub S over V sub O is equal to P sub O over P sub F. Alright, now since this is the one that we are looking for, so we have the given things for this two over here. So we have so object, the iceberg, so we have 917 kilogram cubic meter. And we have on the other side, we have 1025 kilogram cubic meter. So it will cancel the cubic meter because rules in operation. So we have 89 or 0.895 unitless. So this is unitless. Now, if you want to convert it into percent, so that will be 89.5%. So it means that for letter A, the answer is 89.5%. That is the volume submerged. Okay, that's the volume of the iceberg that is submerged under water. Now, how to compute for letter B? Now, in order to compute for the letter B, so the volume on the surface of the water, right? So the volume of the iceberg in the surface of the water, in order to compute for that one, we need to subtract. Alright, so we need to subtract the total volume. Alright, so volume total minus. Alright, so total volume minus the volume submerged. Right. So what is the total volume? That is 100%. Alright, minus 89.5%. So what will be the volume that is on the surface? Right? What is the volume on the surface? Right? What is the volume of the iceberg that is on the surface? So that will be 100 minus 89.5. So that will be 10.5%. Right? So that will be 10.5%. So it means that, what does this answer means? It means that there are greater parts of the iceberg that are submerged, 89.5 of it, And the one that we see above, alright, so the one that we see above is just only the 10.5% of the total volume of the iceberg. Okay, so that's how we compute mathematical word problems related to partially submerged object. Now let's take a look at the second word problem. Alright, so in this case we have mercury, alright, as a fluid. Okay, the metal block floats on liquid mercury, which has the density of 13,600 kg per cubic meter. If 70% of the block submerged in the fluid, what is the density of the metal? So in this case, we will try to find out the density of the metal that is submerged in this mercury. Okay, it is not the actual metal as stated on the problem, but we can work on it. Alright, so somehow this picture works out. Alright, so let's solve for this problem that we have right here. Okay, so what are the given things that we have? Okay, so the given things that we have over here is the density of the mercury, which is 13,600. Okay, so 13,600 kilograms per cubic meter. Alright, so we have the portion of the block that is submerged, that is 70%. Alright, so it means that the total volume, so the volume of the object should be somehow 10. Alright, 10 cubic meter. Right, so the volume of the object, we will assume that it is 10 cubic meter. Why? It's because the submerged part of this object is somehow 7 cubic meter. So it means that this is 3 cubic meter and the submerged part is 7 cubic meter. Alright, so why did I use 10? Because somehow it is very intuitive that this 10 should be the volume of the object. Alright, so now we are asked to find out what is the density of the object that is placed on the mercury, like the one that you have right here. What is the density? Again, we will use this formula. TF times VS is equal to TO times VO. Okay? Alright, so since we are looking for the P sub O, so we can arrange this formula as PF VS over V sub O. Okay, there you go. So let's substitute everything. 13,600 kilograms cubic meter times, alright, so times, so the volume of the object is somehow right, so the volume of the object is 10 cubic meter over 7 cubic meter, which is the volume that is submerged. Alright, 7 over 10. Okay, so multiplying this one, we get 13,600 times 0.7. So that will be, or it will give us the approximate density of 9,520 per cubic meter, kilogram per cubic meter. So this is the density of the unknown object, which is, or the metal that is submerged on the mercury, right? So this is the partially submerged object, or the metal, the density of the metal that is partially submerged on mercury. Alright, so let's go to the third and last problem that we have right here. Okay, so ice has a density of roughly 0.9 grams per cubic centimeter. And the water has a density of about 1.0 grams per cubic centimeter. Approximately how much this time there is a dimension on the iceberg? Alright, how much of the 100 meter thick iceberg will be located above sea level? And assuming that this iceberg melts, how much of it will be above sea level after the half of its mass has melted. Okay, so let's solve for this one. Okay, again, we can use the fraction. Okay, so we can use this formula. So V sub S over V sub O times P sub O over P sub F. Alright, so let's substitute everything that we have right here. Okay, since we are looking for this, we can have 0.9 grams per cubic centimeter over 1.0 grams per cubic centimeter. Okay, so definitely it will give us, okay, so this will be our volume that is submerged, right? That is the fraction. 0.9 over 1.0, that will be 0.9. Alright, so that will be 0.9. Okay, so that will be 0.9 and dimensionless. Alright, or 90%. Now, we will multiply. Alright, so we will multiply 90% with 100. Right, so we will multiply 90% with 100 to find out how much of the 100 meter thick iceberg is located above the seawater. Alright, so 90 times 100, 0.9 rather, 0.9, right? So 0.9 times 100 meters will be, okay, so that will be 90. Alright, so that will be 90. That is submerged. Alright, that is submerged. Okay, 90% or 90 meters of the iceberg is submerged. So it means that the one that is on the surface, is 10 meters. Alright, so it means that the one that is on the surface is 10 meters. How did we get 10 meters? Right, so how did we get 10 meters? So we subtracted 100 meters, the total dimension. Alright, so the total dimension of the iceberg subtracted to the volume submerged, that is 90. So we get the volume of the surface of the iceberg above sea level is 10 meters. Right, so 10 meters. Now, how about the second question? Assuming that the iceberg melts, okay, especially we have global warming nowadays. So if the iceberg melts, how much of it will be left above sea level after half of its mass will be melted? Alright, so let's replace 100 with 50 meters. Alright, so what is the volume submerged at 50 meters? Alright, so 0.9 times 50, that will be 45. Okay, so 45 meters. So 45 minus 50. Alright, so 45 minus 50, the volume of iceberg on the surface is 5 meters. Right, so 5 meters. Okay, there you go. So that is the word problem for the partially submerged object. Now my question to you is the iceberg, okay, can we use the iceberg as an analogy for isostasy? Alright, so let me know in the comment section on this video if we can use the iceberg as an analogy on how to explain or how to understand how isostasy works. Alright, so definitely icebergs are good examples of isostasy, and the iceberg itself is analogous to crust, and the water in which the icebergs are floating, this is the mantle itself. So they are analogous, but in terms of density, they are completely different. But the way it looks, the iceberg, alright, the way it looks floating above the water greatly show us what isostasy is all about. So as you can see right here, okay, as you can see right here, if the iceberg is melted evenly, alright, and half of it from 100 to 50 meters and half of it suddenly melts away, okay, the volume of the surface or the volume of the iceberg on the surface is still around 10% of its total volume. Right? So that is 10% of its total volume. So that is the partially submerged objects. Alright, so after we used math in finding out the partially submerged object and somehow use math in order to explain the variation in the topography in here on Earth. Okay, so in this case, we were going to ask a question, how high is too high? Alright, so it means that is there a limit in terms of height of a mountain? Is there if there's something or is there a factor that limits the height of the mountain? Or should I say, is there a factor that limits the depth of a certain ocean basin? Alright, so let's try to find out in this experiment that I have right here. Okay, now in order to explain this one, let's have an analogy. Okay, if you happen to see a cargo ship, the one that is the big ship that has a lot of cargo on it, cargo vans, right? So you can use that analogy in order to explain this phenomenon that we have right here. Now, the question that I'm going to ask you, aside from how high is too high, is when the Mount Everest, for example, when the Mount Everest is subjected to weathering and erosion, right? When the Mount Everest is subjected to weathering and erosion, does it increase in height or not? Alright? Will it increase in height or not? Okay, so that's the question right here. Now, in this experiment, I placed a bowl. Alright, so I placed a bowl on the water and the level is recorded over here. Okay, so the level of the water and on the bowl is recorded on the bowl itself. So this is the line that you have over here. Okay, so as we can see, the bowl is not loaded, okay, with materials inside. Okay, the bowl is not loaded. Now, okay, so in this portion or in this part of the experiment, I will try to put a beans or put some beans inside the bowl itself. So what do you think will happen if I put beans inside this bowl? What do you think will happen to the marked layer that you have, or the level that you have over here? Okay. Alright, so if your hypothesis, alright, so if your hypothesis is it will sink, then definitely you are correct. Okay, because as we put some load inside this bowl that you have right here, as we put some load inside this bowl, the tendency is the overall weight of the basin, or the overall weight of this bowl, increases. Just like your mountain itself, alright? Just like the mountain itself. Once it experience pushing force, okay, it will increase in height upward. Once it increase in height, it will sink deeper, alright? So it will sink deeper down the bottom. So it means that as the mountain develops, or as the mountain grows in height, also the roots of that particular mountain also grows below. Okay, so as you can see right here, as I okay, now as I increase the load, alright, so as I increase the load of this bowl that you have right here, the level that was on the level that was located on the surface of the water earlier is now submerged at the bottom. So it reflects that the weight, alright, so the weight of the mountain should be equal to the buoyant force that is applied by the mantle to the mountain itself. Alright, so that is the key idea here. Now, Okay, so at the end of this portion of the experiment, so the marked part of the bowl is completely submerged, and the beans are already inside this bowl. So what does the beans represent? Okay, what do you think? What do you think the beans represents in this experiment? Okay, let me know in the comment section. What do you think does the beans represent in this experiment that we have right here? All right. So these beans represents the rocks. Okay, the rocks, the materials that makes up your mountain. All right. So the granite, the boulders. All right, including the ice itself. All right. So including the glaciers on top of the mountain. Alright, they are represented by the beans and the corn kernels inside the bowl. Now, the next question here, what will happen? The next question here is, what will happen if I unload the materials from this bowl? Alright, so I remove these beans and corn kernels inside this bowl, one by one. Or rather, I pick, or I will scoop some portion. Alright, I will scoop some portion of the kernels and the beans inside this bowl. What will happen? What do you think will happen? Alright, so let's take a look on the next experiment. Okay. So I start to unload those beans and corn kernels one at a time. Alright, so as you can see, there is a slight changes in the level. There's a slight changes in the level as I unload. Okay, so earlier it was below this this line that we have right here. It is completely submerged. Now it starts to rise up. Hey, it starts to rise up. There you go. Okay, so it starts to rise up, and eventually, if we completely unload these beans, okay, if we completely unload these beans in this bowl that we have right here, it will go back. The line that we have right here on the bowl will go back to its original position. All right. So the question here is, what does the removal? All right, my process. What does my process of removing the beans inside the bowl represent in real life? Okay, what does it mean? Okay, it means that this process, the removal of the beans inside this bowl, represents the factors. Okay, it represents the factors that that is affecting the growth of your mountain. Alright, that is affecting the overall increase in height of your mountain. Okay, so it means there is a limit. Okay, so what are those factors? Number one is, okay, so the unloading process can be done by erosion. Alright, so erosion by wind, by water, alright, animals, something like that, humans, okay? Alright, and also we have weathering. Okay, so weathering can be caused by chemical weathering, alright? So water, something like that, or mechanical weathering, something like that. In which small surface area, alright? Rocks with small surface area become larger because of weathering. So erosion and weathering. Now, and also we have another factor which is called the gravity itself. Okay? So these are the three things that limits the height of the mountain. Okay, these are the three things that limits the height of the mountain. And also, if we can add, if the mountain has glaciers, if the glaciers melted, yeah. So if the glaciers melts, okay, on the top of the mountain, it also contributes to the changes in the elevation of that particular mountain region, right? So in this case, we can call this one as changes in the elevation. Okay, for example, the original region, okay, is made up of mountain ranges that you have over here. So as we can see right here, the mountain tops are over here, and also if there are mountain tops, there are also roots of that particular mountain. Okay, so these are the roots of these are the root of that particular mountain. Okay, as I've said, the higher the mountain, the deeper the root system that the mountain has. All right, now it is submerged on the upper mantle. So this is the upper mantle. Okay, so this is the upper mantle, and because of isostasy, the crust is floating above the upper mantle. Okay, now because of erosion, okay, by wind, by water, all right, by animals over time. Okay, so because of erosion and the relocation of materials like rock, soil, all right, so the relocation of soil on this side of the mountain and also on this side, okay, happens to be changes the elevation of that mountain area. So the roots that are situated at the bottom will now go upward. It will experience a force or uplifting force. Okay, it will experience an uplifting force once the portion. Okay, so once the portion of this mountain unloads, once this portion of the mountain unloads, the roots of that particular mountain will go up. All right, it will go up in reaction to the decrease in overall weight of the mountain itself. Okay, so it will go up just like what we have on the previous experiment. So as I unload the beans on the bowl, all right, so the buoyant force will be exerted to the bowl, and the bowl will go back to its original position. All right, now what will happen to those places where the materials from the mountain is relocated? For example, this one. Okay, so the materials from the mountain, all right, we called it deposition. All right, so this is now the new place, or this is now the new position of the soil, the rock, and other materials that comes from the eroded mountain. So that one will increase its weight and it will sink. All right, so the reason why this particular part of the picture sinks at the bottom, it's because the weight of this crust is increasing. Okay, meanwhile this part, the weight of the crust is decreasing. That is why it moves upward. Okay, it moves upward. Now, with the action of the force coming from the mantle, the buoyant force that is coming from the mantle, it pushes the continental crust upward. Now, as the mountain continues to erode, all right, as the mountain continues to erode, it will continue to uplift until no more roots, okay, until no more roots are found in that particular mountain. Okay, and the mountain, is it possible to make the mountain a completely flat land? Alright? Is it possible to have that one? Yes, it is possible. Okay, from mountains to plains. Alright? So that is possible, but it will take a longer time for it to happen. Okay? So that is your process, and we called it isostatic adjustment. So it means that the mountain itself is only temporary. Okay? Now because of erosion, weathering, and also gravitational pull, all right? Because of those, and also don't forget melting of icebergs, or rather glaciers, yeah. Okay? So don't forget the melting of glaciers. Now because of that, mountains are not temporarily said to be as the mountain's height is only a temporary process. Okay? It is only a temporary concept. Okay? Now, if you add erosion, weathering, and other stuffs and factors, the mountain will likely to increase in height or decrease in height depending on the gravity of this factor. Okay? So for example, we have right here the erosion. Okay? So because of the uplift, okay, so the roots will go upward. Then those sediments that are relocated on this side will sink in the process. So they are opposite in direction. So this one will sink and this one will uplift. Again, the reason why this one uplifts is because the overall weight of the mountain decreases. And meanwhile, this one sinks is because the overall weight increases. Okay? So it means that landforms that you see here on Earth are not permanent. Okay? They are temporary. Okay? And because mountains are subjected to erosion and weathering, these particular factors contributes to the decrease in height of the mountain over time. And eventually, from a mountainous region of a particular place, there is a slight or there is a complete change in elevation of that particular place. And thanks to isostasy, this is possible. Okay? Right. So now this thing is possible, that the one that we have right here, isostasy is possible because of the differences in density and thickness of the crust and then the mantle. Okay? So differences in thickness of the crust, the continental crust and then the oceanic crust, and differences in density between crust and then the mantle. So because of their differences, isostasy is possible. All right. Now, let's go back to oceans and continents differences. Okay, why does the ocean basins dip? It's because its oceanic crust is somehow denser and thinner. So it sinks deeply, all right, into the mantle. Meanwhile, the continents are thick and less dense. They float higher above the mantle. So, this is your continental crust, and this one is your oceanic crust. Again, the basic idea here is if an object is less dense, it will float higher on a fluid. Okay? So it will float higher, just like what you have seen a while ago. Alright, so that's the reason why ocean basins will never be shallow. Alright? Ocean basins will never be shallow. And continental crust, alright, mountainous region will somehow continue to increase its height as time passes by, and it will decrease in height if there is no roots. Okay, if there is no roots that will replace the one that is eroded on top of the. Alright, now to end up our video lesson that we have right here, this is a simple life lesson that we have. Okay, people around us always look at success the way we look at the iceberg. Okay, so the one that you have right here, success is just only a 10%. Okay, that is only a 10% of what we see. The 90% of success is located at the bottom of the iceberg. This is the 90% in which people cannot see. Okay? So because of in real life, there is no such thing as isostasy. So this thing will just go up. No one, or basically, or in real life, in reality, no one no one will saw your struggle when you achieve your success. Okay, because 90% of it is submerged at the bottom, and what people sees on you, okay, what people see on you is only just the 10% of your success. All right, so with that, okay, that ends up our video lesson for this session that we have right here. Okay, so I hope you did learn something from this lesson or topic that we have right a while ago. Okay, so this is the isostasy. So if you did get a value from this lesson, so just hit the like button and subscribe to my channel, and don't forget to hit the notification bell for you to be notified, okay, whenever I upload new science video lesson in the future. All right, so this has been the Sir Ryan, okay, and this is Science 4K. We'll see each other next time.